Hi, everyone. Hear me? So I think that screen is broken again, so we have to rely on this white screen. And the schedule is shown in the right-hand side of this screen. So for around the first half an hour, you will finally have access to our tutorial questions to answer this question by yourself. And the answer will be released 11:30. And after that, I will spend around 10 minutes to walk through all the questions and explain the answers. And the second part is paper reading. So in this time, we will read this paper, Hardware for Machine Learning Challenges and Opportunities. This is a paper from MIT, around 10 years ago. And you will be given around 30 minutes to read this paper, and we will have like the paper discussion. And as I mentioned last time, in this paper reading group, I want to make it a bit different. So instead of I introduce all the way throughout the whole session, I try to pose several questions at the left-hand side of the screen. So you just try to read all these questions, so you try to read the paper, and we'll have the discussion together. So this is the schedule of today's tutorial, and just start the answering part first. Do you know? He's the student working with me. Just let you know. Let me know if you don't have access to the tutorial. People just comment, the schedule is shown this slide here. it's not. Have a look at the slides. It's pretty straightforward. A and B settings. One go more this kind of stuff. Both A and B files, they are skewed to either any one side or the other. As a result, you don't get C. It will be as so it's let's have a look. C. It's the result that point is all the input are and from smart cycles is A11 is fed in the first cycle, and then A12, A31, B21, B12 fed in the second cycle. So which cycle this is gathered through. That you kind of pretty much get figure out Let's just say right now. It's not in the Excel. It's not in the Excel. Not exactly. Yeah, like that way. I believe he's per cycle, right? Yes. As in, like, check after how many cycles become the first value. Also, like the first fashion accumulation. How it comes off the. I think it's like this. So if we, for example, A11 accumulated results. Anyway, what will you tell me your answer? I'll just look at the thing. It will go through C11. Yeah, it gives a weighting. 3 blocks. It's a binary question, so it's not volume, it's not a formula. So that's like one element of C matrix. So it's not C matrix. Our 3 cycles results should be here. Yeah, it should be okay. Similarly, if you just serve the so after 3 cycles as well. See, it's not one so we use every few just eventually. At least I think this is origin.
Okay. I think there's nothing about risking the other one. So you could reset the thing, but you'd have to do the whole panel. So 10, 15. That probably best to accept what you've got on my laptop. I think that's it's got a red light on there, which means what's happening here. it's all sort of like pretty much do that, shut down, type again. But,
maybe just up to.
yeah, but I'd say, I mean, most of the things are going on.
Is it? I think it's. I think it's the functionality. First one. It's true. Yeah, I think after one.
Oh, this is for you.
Is there any type of this one is fully unwritten. This is an intro. Between the arrays because I think this one it will be doing this array customers go. So what's the difference? This one, that one, this one is this, that one is it is just an array how. What? You know any?
Yeah.
You can ask.
I don't know if it's.
Is it going down? An array.
I just assume this.
I think. Do you understand the question? Could you just repeat? So this one at this direction? This one at this one.
Just the offset to get to that.
Look, it's going diagonal. It's offset by X and offset by
Like, what is the type for?
Must be.
yours. If they're the same coordinates, then it's
Let's specify.
It's one dimension.
I don't think. 0 to block.
3 or 4 to 5.
And then like the mask.
The mask,
Dimension trying to explain.
I guess
the mask just takes it from its until the max. I don't know.
Yes.
offset
Try to
false
Oh, it just
when
keeps.
array
the offset is larger than x.
shape of 2.
So that it
Try to expand this guys.
I think it just keeps.
Direction to expand.
Yeah, I think
I think it's not even the question.
I don't know how it's
Use the single Python. I think we try to use everything. Try to print out. Try to print it out. You realize what's going on.
comparison.
I think it just keeps anything less than. I don't think it's a boolean. It basically keeps anything.
The mass would,
okay.
the mass would be a boolean filter, and then that would just return so every time that it's larger than.
Okay.
So I assume that
Yeah, no, you're right.
cuts it off.
You can try. It's just the best
So it does a
try
boolean.
programming and print it out.
Yeah, and then I guess it just cuts anything larger than 1,000. Assume if that's the dimensions.
Okay, I get it.
That's my guess.
It's just 2 dimensions.
Well, fine.
Yeah, it's 2 dimensions.
So I guess okay, so that would be.
So that's how it would do it.
It's still like broadcaster.
Yeah.
That.
That meant like. This is.
I think for each. Yeah, for this one.
Because in our final exam, I will not ask any Triton program related questions. So if let's say it's too difficult for you to understand, you can just go to the third question. That is the focus. This is the story array.
Assume.
Yeah, you get a bit of one.
So it cuts off.
Yeah. Used to be a row, right? To view all the.
And the last 24.
Oh, that could be false. False was lost in true. First,
Yeah, anything less than 1,000. Anything less than 3. Yeah, that's false. So
even
you'll
though that's. I guess yeah, that's just how.
Yeah, it's just a comparison.
The example, which goes with.
got off by 1, but I'm gonna count the cycle starting from 0 rather than 1. But anyway, these results come out at the same time, right? This guy is index 2, 0. This is 1, 1. This is index 0, 2. Sum them up at the same. So 2 plus 0 is 2. 1 plus 1 is 2. 0 plus 2 is 2. They do indeed come out at the same time.
Yeah, I mean, it shoots a plural.
These guys come out at the same time. This guy is 2, 0, 2, 1, 1, 2. Sum them up, they're both 3. They do indeed come out.
Yeah, that makes sense. I mean, I'm getting tripped up because it was like you do the multiply one step, but then the add the other.
Are you doing them on the same step? Yeah, they should do it. Okay, yeah, they're on the same step. Yeah. I got the same thing, just off by. I started from cycle 0 with the empty state. That's all.
Okay.
Yeah, but then otherwise I would get the same thing. What?
Like all of it. Just like so confused.
Looks right. I mean, kind of. Just diagram. So
Yeah, no, this.
Oh, 2. Okay.
This is 2.
Okay,
Yeah.
I'm still doing 2. I haven't done it yet.
No, this. I feel like I got it.
Okay.
Yeah. I'll see how he explained.
Oh yeah, I drew this. This is Fig Jam.
It's nice though.
I feel like we go through a row. Perfect. And then be like, it's just in rows. Column or something.
Let's see, I did this. Second one is that. So I need 3 cycles to get the first one done. So saw that you can't do it now. You have to wait until it's cleared. Then you can start to drain it one by one. This guy gets free.
But the placement.
Able to leave this first one.
Load of that from the reading.
Next line.
Maybe it's like this. Do that for that.
The next one, like, I'll do it next. I haven't done for the last.
Soon.
Don't they all become? If this was not 3 by 3, then you would need that, but
Technical.
3 by 3,
I need to add the suffix.
Yeah. So I think perhaps if your practice to just optimize this group, look at how tension is. If let's say you also do some block tower in the end. So my understanding is your conception.
For data flow.
Look at how we let's update. They kind of have this. Okay. This is related to the construction. I ask you.
Just to ask.
Yeah, the tension on this group of applications. It was very effective. Thank you. I guess it might be a bit if you are very. I think the reason is just systems are powerful. First evaluate it's really it was years. I think I think if let's say is to accelerate. This can count as one. Yeah, that's just yes. It's not. It's just whether the calculated model is makes sense or not. One doesn't one try to accelerate. It's the same way. So they want the algorithm cell. It's there. So you focus on the future. So that's it.
You know it's easy to fix it for
Think about this good input. Like this.
I am still working through this.
Are you doing?
Yeah, I'm doing try to.
Oh, wait.
Oh yeah, something like
I
that.
know. I was looking at that. I was like, that's like what I did. I'll let you cook.
Okay, I'll
Yeah, sorry, I'll shut up.
Sorry, I have to provide a cook.
So honestly, they will.
I'm so confused. Like, I don't get it.
B00 plus 2. Meanwhile, PE0. Think of one input. PE00.
Can you access the answer?
Cycle.
I'm going to see question one get up.
Still the epigenetics.
Interesting. be like the first one.
Draw that.
Yeah, it just goes, yeah, it's canonical.
You will have to figure out why would that be information so architecture or something like this. Assume they arrive at different cycles.
So what ends supposed to be?
No, I feel like it's not mentioned.
Since by one.
Yes, 8 watches.
Just assume that this is the same.
You can make this one.
384511.
I think it's before that. Yeah, we don't know what X or Y was. So, then, before we even get
Oh, we're just actually just describing.
Yes, I think it was.
the later one, actually.
It looks very confusing saying it's stationary.
Another thing is
Be true in that range.
Let's watch it again.
No, not necessarily.
Cycle.
Just because that's the lowest value.
Yeah, it's 8. Oh, we don't know.
Not the value being processed, but it's A00 being fed to the next P. So the accumulated result is stored in this P, but not passed to next P. 00 not passed to B0, whatever is not passed to they are joined starting basically.
There. This guy go this way. What do you got? Yeah.
I literally only got that though because it's in C like explained like why this thing's better than row major sweep, and I was like row major sweep, but I like don't really understand.
Did you try doing the modulo and
The modular one.
Yeah, so I did like an example for this. Like I drew out,
And then the division.
and I was like,
Oh, you should do 7, 8. Like you should just do a series of them, like 0, 1, 2, 3, and then see how it changes. Do 0, 1, 2, and 3. All of them dealing divide to the same to the same number.
yeah, because that's the same row. Like if I do 0, 1, 2,
Finding readiness
it's gonna be
Divided by 4 will all be row 0.
Zero.
Yeah.
Yeah.
Okay.
Yeah.
Don't really care about when you
that makes
outside
sense.
of the check.
And then the modulo will keep on incrementing.
There's no writing.
So the n will keep, yeah. So 0, 1, 2, 3 will be in different n's.
Yeah. Okay, and then
Think about B.
I just started with
A00B. This result
Should we start? Or do you want us to
safely
by ourselves?
the value itself.
So let's get started. So I will start from the third question. Because as I mentioned, this historic array part is accessible, and I will link the Triton later if we have time. So let's start from this historic array. So you have 3 times 3 by 3 historic array to compute a matrix multiplication, and the question asks you derive when this, for example, the Cij, which is the output one of the output elements index using I and j in this output matrix when these outputs will be ready. And so as you can see, the exact calculation to get the number of clock cycle when this number ready is shown in this slide. So you first need to count how many clock cycles when the data stream into the corresponding PE position. So if you look at, I hope this animation is very easy to understand. So let's just look at the PE at the index 0, 0. So this is PE 0, 0 here. So how many clock cycle when the result is ready in this PE? So basically, you will first need to count how many clock cycles the first input and first weight arrive on this PE. And then you just calculate, for example, in here, the inner dimension is k is equal to 3. And you kind of calculate k clock cycles to get the final answer. For example, in the first PE, so basically, the first input is ready at the first clock cycle, right? So as you can see here, so the result is ready, and you keep advance to the next clock cycle with 3 calculation rounds to calculate each element, because in this matrix multiplication, you need to accumulate along the k dimension. So you need to do matrix, or you need to do multiply and accumulation 3 times. So this is the formulation of calculating how many clock cycles you need until the result is ready in particular PE using this IJ index. And another question, maybe extend this a bit. So how many clock cycle you will need to get all the result ready in this historic array? So this is not asking this question, but how to derive that number. So basically, you just need to get the farthest PE, right? So to calculate how many clock cycle will be needed in this historic array. So basically, you will need to ensure all the results are ready. So to calculate this clock number, so basically what you need to do is you need to look at, for example, in here, the farthest PE when it's ready. So you just put this, put I and j into this formulation and get the number of clock cycle when all the result will be ready. And in this module, we assume once the result is ready, it can be trained out immediately. There's no write delay. So this is just to make the problem simple, which means, for example, in this historic array, we assume this PE, let's say this is your right port or this is your output port. So you basically connect this PE to each output port. So there's no, for example, you don't need to use the register inside each PE to propagate this output result. Once it's ready, it's just kind of streaming out. So this is kind of, in small scale, it's possible, but if you're talking about, let's say we have a 100 times 100 historic array, this kind of wiring is not scalable. But this is just for help you to understand the whole idea of this historic array and make things simple. And let's just do a follow-up question. Let's say if you have a historic array, for example, is n numbers of row and n numbers of column. So how many clock cycle for all the results are ready in this historic array? So the formulation is first, so just according to this formulation, just according to this formulation, right? So let's assume you have a matrix multiplication A times B, and the shape of A is M by K, and the shape of B is K by N. So you kind of, and you use m times n successorial array to calculate this matrix multiplication. So basically, the number of clock cycles you need for all results already is basically, because in here we use the zero-based index, right? So if you count this, the total number of p's basically is m minus 1 plus n minus 1 plus k. So this is the total number of clock cycle will be needed in an output stationary systolic array. Clear, right? There are some other variants, as I mentioned, variant of streaming flow. For example, the weight stationary. So the paper we will visit in today's paper reading group. So it's basically, the original paper is how to optimize the convolutional neural network on this systolic array. So basically what they're using is weight stationary stream flow. And I also put a link, if you look at the reading group slides, I also put a link to explain how the weight stationary works. And it's kind of homework for you to derive the total clock cycle for this weight stationary systolic array. Yeah, try to do that. It's very important. So this is the third question, and we only have 3 minutes left. But let's at least go for the first question. So this is I even think I shouldn't ask you this question. This is very simple, right? So given the total number of elements, and you have this program, you basically just assign a real number to these variables to get this global index. And the reason why I asked this problem is just to kind of to tell you, like, this masking is used to control a boundary. So you always need to have this masking operation to ensure like you have the good boundary control for your matrix multiplication. And for the next question, do you want me to explain this one, or you think we're fine to go to a reading group? Yeah. Okay. So basically, this is how we assign this 2-1 is how we assign this instance ID to the PIDM and PIDN, right? So let's assume as I mentioned before, so this, let's assume we have an instance ID which is 1D vector. This is 1D vector, so this is PID, PID1, PID2, So what it's doing here is it trying to convert this one vector of instance ID to a 2D instance ID. So basically we kind of convert this 1D vector. As you can see here, it's get from this program ID, right? So we kind of convert this 1D vector to a 2D. So the way it's doing is, so it's first divide by this V. So this V is determining how many numbers of blocks in this tile. So basically what we are doing here, we convert this 1D vector to a 2D vector, and this dimension is M, this dimension is PIDM, and this dimension is PID. And so we have, for example, M, and to index inside this 2D vector of program instance. So this is clear, right? And if you try to increase this program like instance ID by 1, you will see the direction it's working is, let's say if you increase it by, let's say it's your V equal to 3 and G equal to, let's say, from Z 0 to 1 to 2, you'll realize the increasing direction is more like this, right? And what this question asks you about is, instead of kind of converting this 1D instance vector to this 2D instance vector in kind of this row by row, can we just have like something in this direction? So for a fixed number of rows, we want this PID go along this direction. So this is exactly what this question asks about. So how we do is, so let's say in the original implementation, forget about this, like the, so when we convert in the original implementation, when we convert this 1D vector, instance vector, to this 2D vector, and we follow this row by row implementation. So the way we write the pseudocode is basically for PID, because this is app, right? We kind of iterate through app. App should be the outer loop, because we kind of, inside one PID, fixed PID, we kind of increase this PIDN. So it's more like for PID M from, this is 0 to app minus 1. And in the inner loop is PID and to n minus 1. So this is exactly how this when this 1D PID is converted to this 2D, how this works, right? And what we want, so remember in Python, the best way to derive this pointer, to do this pointer arithmetic is write the pseudocode first and kind of get the pointer address. So in here, this is our naive implementation. And what this question asks you to do is for fixed number of column, try to iterate different groups of PID. So if that question asks you to do that, so first convert this pseudocode into, for example, so let's say the question asks you to kind of do for fix of column, right? So in here, what we need to do is we need to kind of change this PID n to the outer loop. So this is the utmost loop for PID, and this is from 0 to kind of to V. So to kind of make the column first, you kind of change the order of this loop. And to do the rest, because you also need to do grouping, so you also need to split this PID M loop. So basically what you need to do is, in the inner loop, you further split the PID M loop into two nested loops. So the first is you first need to iterate different groups of rows. So basically in here, you have for example, GM in, let's say, sorry, so 0 minus 1 to, for example, GM. And GM representing how many, if you look at the answer, the code, the GM representing how many kind of groups along you have along this row direction. And inside this group, you have another index, which is K. A K in this 0 to this kind of block size of M inside one group. So if you can see here, so in the result, so it means how many elements in one group of M row. So it's block size of kind of G. So you kind of have this, you kind of change the order of M and PID M and PID N to make it as kind of column by column, and you further split this M to make it kind of do some grouping as requested by the question. So you kind of get this pseudocode, and you can get this PID M equals to, if you can see here, is GM times this kind of block size of G plus K. So this is your PIDM. And when you try to kind of flat these three nested for loop, you'll kind of get the equation, which is, let's say G. G is basically equal to, let's say, if you first flatten the first two loop, so we'll realize is, let's say, assign this is Q, which is the Q variable in your exam question. So it's basically, according to this, it's PID n times number of blocks in the next group times GM plus this GM, right? And this is a Q. And when you flatten this Q, you will have the Q times number of elements in this block, block G, times block G, and plus K. So you have this index. As you can see, this is how we get this answer in our example, in our answer code. So basically, first we need to get this G, and we get this Q. So basically, to get each pointers, you just kind of divide them one by one to get this code. So for G, so it's basically this, if you have this equation, you can easily get the Q, the formulation of Q. Q is basically G, according to this equation. So Q is basically, because as I mentioned before, Q is the flattened index of variable after the first two loop. So basically, you just divide by this group M, which is the block size M, here, and you have the modular. So this is this question.
What does this give us for element-wise addition, though? Because the question is asking about caching, but for addition, we don't need to reuse elements. Like, if we're doing like multiplication, I get it, because you're reusing elements along like multiple times.
No, I think this question is basically just ask you about how to do this group M.
And then, but the follow-up in C asks about
yes.
caching. But what are we caching if we're not reusing elements? We're doing element-wise addition.
So I think we'll do vector F. Let me check. You still need to read the data, right?
Yes.
Yes. So that's what the second question asks you about.
Right, but you only. It's not like in a matrix multiplication where you can cache a tile and then you're reading from that tile rather than from memory. Each value you read, you're only using once. So caching doesn't give you any benefit if you're doing element-wise addition.
Yeah, exactly. Yeah, so we need to make this as the multiplication. Yes, if this is just the element-wise vector addition. Yes, you're right. Yeah, I think the problem is in the last question I asked here, I asked you to explain how this add to cache is affecting this, how this grouping strategy is affecting this L2 caching. And the problem you just mentioned is because this is a vector addition, so it doesn't matter because we just load it once and we're not do caching. So this add to cache will not help you to. We're not try to like read multiple times and do caching. And if this is kind of a vector addition, so we need to do like it will not have a big impact of this add to cache utilization. But so the point I want to ask here is, for example, if this is kind of matrix multiplication and you do block tiling, so what you need to do is you still need to load data multiple times, and this grouping might be very helpful. And this is corresponding to the code example I gave in our lecture. So all this indexing I calculate here is basically the same as the blocked program of matrix multiplication, the third example I gave in the lecture. So basically, what I explained here, how to calculate this group M and how to do this group indexing is basically if you use this third question to the matrix multiplication example, it still have the huge benefits in add to cache. Okay, so this is the end of tutorial session. So let's just take 5 minutes break, and we will have around 25 minutes paper reading. And this is the question we will kind of discuss in our paper reading session. So some background about this paper. So this paper was, as I mentioned before, was written around 10 years ago. So it's basically after the first wave of deep learning. So this group from MIT, they wrote a paper called Iris. So it was very popular and famous at that time. So in this paper, it's basically a follow-up paper based on their first version of Iris hardware. So basically, they just summarize different challenges and opportunities and future directions. So let me know if you don't have access to that paper. So the paper looks. Yeah, so the paper looks like here. Jim, yes. And I think I shouldn't make this vector addition because the L2 slide, I think you just mentioned, is if that is just vector addition, we just need low one time. But when I designed this, I just want to make this as simple as possible, and I changed the setting. I forgot about it should be matrix multiplication.
So what's happening? Yeah.
You can increase the block size of M. But
I think we find the
we discuss now.
The whole thing lives in one line.
Yeah. If let's say, I think the key point of this question is use this grouping to improve the L2 hit rate. And yes. If that's my yes. At the beginning, I just want setting as two.
Oh, really? In the next chapter. I see.
Yeah, because in the original slide, I think
Actually, that's only course, no exam.
I think it's clear.
It's all student.
Yes, because
You did
I have the offset. Yeah.
Might be. Is it difficult?
Okay, so this zero.
It's very math heavy.
Okay. Sure.
Maybe I can post something about this time.
Yeah, sure. That'd be good.
Does it have
Regarding the six-story arrays, this is very important. It's likely you will have this exam. So
any industry that
So ensure it's not likely, I'm just saying. So just ensure you understand how it works. We have so many concepts, so I'm not sure which to put, but this is one possible. So we will have kind of offset here, right? So as I mentioned before, to ensure you kind of get the item at the right clock cycle to do the accumulation. So you basically will have this offset before you feed into this array. So which means, let's say at this position, the second row, you will need to kind of have offset of 1. So that's the reason why we have this I plus j. We call it warm-up streaming, which means this I means how many elements we need streaming in. So how many clock cycle we need the inputs. Let's say this is the second row, second column. So this I means how many clock cycle we need to wait until the data from up coming down, or from down to up. For example, this is the A11. And you also have this offset here. So which means you also need to plus this J. So if you look at the animation I made, you understand. Try to decompose this I plus J into I is the number of clock cycle you need until your elements arrive the corresponding row. And J is the offset introduced by this column, because you need to have these. You need to have this, as I mentioned before, you need to have these right inputs accumulate together at the right clock cycle. For example, in the first clock cycle, the data is not kind of streaming in. You can see here, only this one and this one stream data in, because you introduce offset.
So if you have n by n, does it mean that at some points you're going to be waiting for streaming to come in from one side, so you're going to have to wait at one cycle? Like if there's if there's different sizes in the rows and the grid, you need to wait maybe longer for one of the streams to come in.
Exactly. Yes.
It's going to be like a delay.
But usually we design this historic as a square, so don't need to worry. In that case, another way to this is actually a good question. If you look at what is the weight stationary. So in the extreme case, if you don't have the equal size on the historic array, let's say you have 2 times 8, and it's better to use weight stationary because you don't need to wait until the data come in. If you use output stationary, you need to add a lot of offset, right? But if you use the weight stationary, you basically just do some preloading of your weights into the data.
What do you mean by weight stationary?
I think I explained in this. So weight stationary, so let's say C state AB string and C is your output, AB is your input, right? So this is output stationary, which means you kind of accumulate these outputs inside this one map unit or one P. So we keep the output state inside your P. And this is A state B string and B state A string. So for example, we call this B state AC string. So in the question, I will kind of explain. For example, weight stationary is AC string or BC string, I will tell you. So, for example, in here, so you basically keep your B in this PE, so you're not streaming your P. So what I said, weight stationary is basically B state, AC string. So it kind of, as you said, if let's say they have uneven size on this system array, so it will need to wait a long offset. So the better way is just use this B state AC string. So I will use the animation later to explain.
Or you need to wait if you have, let's say, 2 by 8.
The question.
Very quickly, but like details.
skewness is determined.
So this is the animation
Weight is
of weight stationary sister array. So I put the link in our second reading group. There's one slide introduces skewness.
Yeah.
I will also try to update it with the lecture slide. So as you can see here, after some preloading, so before at the T0, you have all the weights already in slides. HV. And basically you just stick to streaming in your activation, your inputs. So which means you don't need the weights to come in and adding offset. So this is the weight.
More count is 3 by 3.
So in output stationary, you need the warm-up time of two streams and adding offset, right? And in weight stationary, so basically you just need the time of the inputs streaming, and you add the preload weights, because these weights you need actual clock cycle to feed them into this sister array. So
we're doing weight stationary or output stationary. Would it, let's say that you had an uneven.
yes.
Would the number of cycles change, or would it be the exact same?
You mean the outputs in the square, right? Yes.
Like to complete the.
It depends on whether you are do tiling. And if there's no tiling and the matrix is equal to the size of your sister array, they are same. But if you're considering tiling, because you need to consider this weights preloading, right? So it might differ. But do the homework to see how.
N is columns. So Y is row major.
No, so, but I'm saying it's row major.
Answer says it's row major.
Yes, it's row major because row major means so if you this by one, so assuming this is PID. This is PIDN. So basically, what you are doing here is increase the one, and you will realize increase the PID. PID was the same. PID should basically staying same. But N and M. Yeah, is that what you so which one will be the original? It's so here it says the column is yes. This column, right? This column, right? This is row. So columns is changed. Yes. So it's row by row. Yes. Consecutive row are grouped together. Consecutive columns are grouped together to form a row. Also, let me know if some particular part you are not understanding in the paper. I can come to you and we can discuss. First, we should start. Has anyone read this paper before? No. So after reading this paper, so let's try to answer the question. So, what is the key challenge in machine learning hardware? Let's say we want build a new hardware for machine learning workload for deep learning. Does the paper explain this? Any thoughts after reading?
And it's a couple. Accuracy, energy consumption, throughput,
Yes.
latency.
Yeah, very good. So basically, they kind of list 4 key metrics here. So basically, for your machine, for your hardware, so you will need to achieve the good energy consumption for your machine learning hardware. And this is kind of decided by, for example, how you design the computer architecture, and how your compiler, how efficiently leverage the underlying hardware, and also, for example, how your algorithm kind of whether it will kind of have good, for example, data reuse. For example, compare with convolution operation to linear layers. The convolution layer might have a better data locality. So this is the first one, energy consumption, and the second one is the area cost. So basically, let's say if you want to have some edge application and you want to kind of limit the area cost of a chip, let's say to, for example, like 100 square millimeters. So there are some area constraint and also latency throughput. And the last one is also, in recent years, people are starting to realize actually programmability and generality are also very important. So this is for machine learning hardware. So, but I think I also introduced in our main slides is actually a problem for any hardware design. So it's always if you kind of take this latency throughput as performance and area, and also energy consumption as power. So it comes back to the concept that we introduced multiple times. It's called PPA trade-off. So how do you design your chip? How do you design your hardware to kind of achieve a better trade-off in this PPA graph? And this kind of depending on the target application, as I mentioned in the first slide, you're not able to kind of use the high bandwidth memory in your mobile phone because there's some area constraint. So these are key challenges: how to achieve high energy efficiency, low area cost, and low latency, high throughput, and also achieving a good programmability. These are 4 key aspects you need to consider when you try to design this AI hardware. And are there any opportunity to address these challenges? Which one is most impressive for you? Which one?
For me, like algorithm and hardware stuff.
Hardware stuff.
Yeah, co-design the algorithms given.
Core design, right?
Yeah.
Yes. Okay. So basically, after this paper was published, a lot of research focused on algorithm and hardware core design, which means only focus on hardware level to improve this PPA is not enough. You also need to do a lot of algorithm level compression, so which is the main topic we will introduce in our next slide. So we'll introduce what is the quantization, what is the pruning, and what is the auto ML, so neural architecture search. They are all efficient algorithms for machine learning design and for deep learning design. So this is the first one, and also this paper was published 10 years ago, and it kind of the real research after that kind of demonstrate like this core design idea is actually valid. Any other you think is very impressive?
Accelerators.
Sorry?
Accelerators.
Yeah. So this is a very good point. So this paper, as I mentioned, they actually based on this Iris design. So they are the first design domain-specific accelerator for AI, which adopting this 6-story array. So accelerator is also very important. And after this paper, a lot of, not after this paper, not because of them, but kind of after the first wave of like the AlexNet and different companies, they start to build their own chip, which is kind of echoing what's mentioned in here. AI accelerator, domain-specific architecture is very important. Okay, so they also introduced many other opportunities like mixed signal processing, like they kind of have the digital analog processing, and recently Microsoft, actually in Microsoft Cambridge, they have a kind of optical circuit for this neural network, which is very interesting. Although it's like in experimental phase and very small scale, but this is kind of just saying people, instead of just traditional digital chip design, people tend to kind of design more innovative approach. Sorry, I don't know why it looked like this. So they will have more kind of innovative approach for this AI accelerator, like mixed precision optical computing. Okay, then just I think we kind of already asked the last question: what opportunities are short term and what opportunities are long term? I think all these digital chip and algorithm hardware co-design, I think they can be categorized as a short term. And for long term, it was still looking for quantum computing, for example, or optical computing. So this kind of answers the last question. And the following, I will introduce this paper in detail. So as I mentioned last time, every time when you read a paper, not just look at this paper itself. Like for the classical paper, you always need to look at like which research group it comes from, and remember this group of researchers, and kind of follow their articles if you are interested in this domain. So about the author information, so this is from MIT group from Vivian. So he's a professor. She's a professor at MIT. So the paper information is this paper was basically based on this ISCA paper, so-called Row Stationary Accelerator. So it's based on this Iris paper, which is, as I mentioned, almost the first AI accelerator in this machine learning hardware domain. So after this first ISCA paper, which is the most prestigious conference in hardware, so they also have JSCC. So the main difference of this ISCA and JSCC, ISCC is whether you have a real chip tap out. Like for example, in ISCA, it's more like you only need to have some RTL and have some functional behavior simulation to, for example, validate on FPGA. And for JSCC, ISCC conferences, they usually need you to have some like real performance when you kind of use some tap out on some particular technology nodes. And these are some, let's say if in the future or in your final year project, you are interested in any hardware or machine learning hardware project. So these are the leading venue in this domain. So as I mentioned, ISCC, JSCC, so they are kind of a cheap conference, cheap venues, which usually need to like have a real chip designed, and you can kind of measure the real performance. So it's like the tap out when you have the hardware design and you do tap out to get a real chip. It's usually very expensive. So so you can imagine like it's very hard to get in this ISCC, JSCC because you need to tap out your chip, you tap out your hardware design. And the other leading conferences, for example, they are computer architecture conferences, they are ISCA, Micro, SPLOS, HPCA. So they more focus on how you design your computer architecture. You just need to basically, you don't need to have your chip tap out. You just basically need to validate your design on FPGA and kind of improve or demonstrate the architecture performance or micro architecture performance of your proposed approach. And there are some other conferences, for example, for programming language, of course, the PLDI, and for electronic design automation conferences, DAC is the best one. And as I mentioned, so there are several key metrics to consider when you do this, when you design this AI accelerator. And this one thing I want to mention is you will see a lot of paper doing AI accelerator, and they are doing kind of streaming processor, spatial processor, and the key motivation of all these paper is basically most of them comes from this paper from ISCC 2014. So it's kind of try to break down the energy consumption for CPU. So as you can see here, the control, this is a breakdown, for example, of one instruction. As you can see, the real computation only occupies a small portion of the power. For the other things, they are mainly just control. And in this control, they're referring to, for example, the instruction decoding and all the logic control. So this is the basic principle of why we need another AI accelerator beyond GPU. Because in GPU, so you also follow this traditional Van Neumann machine architecture. So you need to do instruction decoding, and it kind of suggesting is very kind of time like energy consuming. So this is one of the motivation why you need to have the domain-specific AI accelerator, not just use CPU and GPU, because they are not very energy efficient, causing by this instruction decoding or the control energy consumption. So so this paper introduced their own AI accelerator. So as I mentioned, so there are different. So the paper, the Iris itself, is a historic array-based accelerator. So they basically have kind of introduced different stream flow for this data for this historic array. The first is the weight stationary, just as shown. I put the link also here, so it kind of has the animation for you to understand what is weight stationary. So basically, before you streaming into your inputs, you kind of have have a preload weights stage, kind of load all the weights to each PE, such that you just need to wait all the input stream coming. And they also have this output stationary and different stream flow. So in the paper of Iris, they propose this row stationary data flow, which is kind of variant of weight stationary. So they basically try to study how to map this convolution on sister array. So remember, until now, we mainly just focus on how to map this matrix multiplication on this sister array. But for convolution, because they have some specific shape of these convolutional kernels, right? For example, 3 times 3, 5 times 5. So how to map this convolutional kernel on this sister array? This is the focus of this Iris paper. Like at the very end of last lecture, I introduced a line buffer idea. This is one example of how to do this convolution. And in this paper, they introduce more. I think they also use line buffer in their design, and they also study this row stationary approach. For example, in here, your green is your weight matrices, and your blue is your blue matrices are your inputs. And basically, you just, for example, in this PE, you just keep one row representing one row from the convolutional weights. So you just keep these weights inside this PE, and you keep streaming in different rows from input to this PE array. So this is a row stationary stream flow they proposed in their paper. And as you can see in the results, so they can achieve a significant reduction when they compile this normalized energy NMAC. So which means kind of they measure the total number of or the total energy consumption, and they kind of divide it by how many like MAC unit they have. It's kind of normalized way to compare the energy efficiency of different architecture. So this means if let's say you consider to a research project related to hardware, so look at all these papers, see how they do this experiment, what kind of metrics are like widely recognized and you should adopt in your own paper. So we have many other normalization techniques when you do this when we're comparing different metrics in chip design, because it's very, as I mentioned, it's kind of PPA trade-off. It's very hard to have one hardware can beat all the three dimensions. So usually what you can do is, for example, just focus on one or two and like demonstrate, okay, you can achieve better energy efficiency, or you can achieve lower latency, etc. And I hope after reading this paper, the key takeaway is it helped you again to understand this PPA trade-off. For example, your design needs to consider energy, area, latency, and throughput. And one more thing I want to mention, I also mentioned before, is the generality or programmability. So one of the key reasons why NVIDIA GPU is so dominating is because they're software ecosystem. And this comes to another problem. Should I sacrifice some of my PPA performance to just gain for the better generality and programmability to enable more users to use my AI hardware? And this problem is becoming more and more important in the machine learning hardware community, because different research groups, they just publish their own AI chip. So you kind of have, let's say, up to 100 AI accelerators proposed by different research groups, and perhaps they didn't explain how the programmability and how the front-end user can leverage their underlying hardware. So this is one key problem. So and I think this is the new research focus for machine learning hardware. And if you look at the there's a startup company, AI startup called Testerant. So they did very well on this programmability. So different startups, they have different strategy for this. And the other takeaway is, I think, is to understand this system array. As I mentioned, it's very important to understand what is the difference between the output stationary and what is different between the weight stationary, understanding these basic principles. And if you look at this paper, this IRIS paper, they just basically propose some enhancement on this weight stationary, so they can kind of get this published. And it's very classical machine learning accelerator paper. And yeah, the rest just some opportunities. Other opportunities I list here. So I think perhaps is the future direction. So the first one is the mixed signal processing. It's still not very popular. So basically, most of the dominating chip, they still use the digital only chip signal processing, like the chip. But I believe this is the future direction, as I mentioned. And I know a lot of startups in Cambridge, they are doing this signal chip design, try to just use the analog signal to process this neural network or computation. And the other direction I think is very, we're getting more and more attraction, is this processing memory and processing in network. So which means instead of just squeezing all the compute resources in one compute chip, you can also kind of offload some computation near memory. For example, you can have some compute memory near your DRAM. So before you're loading data in, so your compute unit in your DRAM can do some pre-processing, for example, to compress the data to ease the memory bandwidth requirements. So this is another direction I think is very interesting, and emerging research in recent years also starting processing near sensor, processing in sensor, and processing in network, processing near network. So the philosophy is very similar. So instead of just for example, for the sensor or for the memory or for networking units, instead of just doing their own job, you can squeeze or design some extra compute units inside these different components, such that you can do some pre-processing before you get data from all these different modules. It can kind of reduce the memory bandwidth, and also it can kind of improve the overall latency and throughput, because you kind of offload some computation to other components. And again, algorithm and hardware co-design. So, for example, nowadays a lot of people are discussing how to use the CGRA, the coarse-grained reconfigurable array, to accelerate AI workloads. And the story is, your AI is evolving very quickly. Like 5 years ago, there's no transformer is not the mainstreaming workloads. It was the graph neural network. It was the convolutional neural network. And if you look at 5 years later, now most of people are focusing on large language model. So this is the reason why the underlying hardware also needs to have some reconfigurability, such that when you your upper level of the algorithm change, your hardware can still be reused for different algorithms. So this is another opportunity, I think, in next 5 or 10 years. And the third one is the quantum computing. So there are already some research papers studying how to leverage this quantum platform for perform matrix multiplication. But again, it's still in the very early stage. But this is kind of an active research direction people are exploring. Yes. So this is the end of today's tutorial session. But feel free to stay here if you want to spend more time to read the paper and discuss with me. But this is our presentation. Yeah. Thank you.
Do you want to wait until the lab starts?
Yeah, no.
You look tired.
It's not that long.
I guess I'm done.
I wanted to do something to be else. I did not change the daylight savings time, so I'm sticking to my old timing. So when I wake up, an extra hour every morning.
That means
Just strange times and construct, didn't it?
We're not concerned, we're just oh my god. It is actually cool. Yes. Friend, yes. Write the group.
Yes.
Maybe
Or you have like
I think actually Jay's here.
I'll give you some. Yeah. Zanto.
Yeah, it is. It's a good question.
I'm gonna eat lunch and then just go to the library. Yeah, how are you? But not any benefit of it. Well, for B answer, like, so B is just a demonstration of this is how. It's just a demonstration that this is how you would know.
Oh no, oh, okay.
Yeah, it's traffic good. I don't know how good it's going to be for climbing, but
So you're all climbing today?
Right.
I don't know how much people are going to commit, because it's like the postgraduates people. Like, I don't know if people are actually like...
But you actually jump. You don't pass.
In this module,
you
just
pass
assume.
that one inches you jump.
Professors, I have a couple.
Minus group and
Not one for this one.
It's late, it's quite late. No.
Scalable system.
Yeah. Scheduling, are you still in that?
You have a whole thing with
Many threads covering.
Okay.
Yeah.
It's okay.
How I think it's how you assign those threads within this two element. That's what gives you.
yeah, but you used to assign PID.
I mean, you can actually...
Oh, so that's what that means. So
It makes more sense information.
oh, so it literally what
So
you
this is
would
the
have
size. I mean, this is
been one process. Here you have this handling that one.
Let's look at how the matrix multiplication works. That will make it clear because that's where it actually. Then you do actually have to do an iteration to do some product to reuse elements.
No, I was only thinking about
You are using
in the idea that it's the same amount of processes.
I signed up for a different at 6.
So it's very simple. Just if you look
The one I showed you.
As in it's the same amount, but no, you have.
The competition.
Also, wouldn't this just be
I already signed up.
doing
I cannot fail.
a major when you have well, it's not sorry instead of blocking you have
it's not.
To be fair, I'm not as comfortable with Triton as I am with CUDA stuff.
So all the steps you just mentioned.
I wanted one
You're
of them.
doing tiled matrix computation in CUDA. So I'm going to compute a tile of the output matrix A. For that I need
will insert the instruction.
tile of C. I need kind of drawn.
And how it works. In your array, when you're streaming data, you have offset, right? You have the offset when you're streaming the inputs.
You have A.
Offset. But for the wins, you don't have this offset because you don't. You just do everything.
Can I also decide which way I
Let's
want
say
to? Essentially, it's really bad, which is flat, but. Can I even say like I want to load it this?
we're computing this tile.
Yeah, you can show.
This is way faster than.
So to do that, what we simply need to do is to take tiles from like row tile and column tile.
You don't need to worry about.
One at a time, we're going to take like tile 1, tile 2, tile 3, tile 4.
You better.
Right, so at the same time, we're going to load this one with this one, this one with this one, this one with this one. When we're loading A, we're loading, like, we're going to do this thing of A, this thing of B. Now this is fine, because if you have adjacent threads access A, they're actually accessing adjacent elements in A, so it's all coalesced. This one, if you do the same mapping, if one's going to access this one, thread 2 is going to access this one, thread 3 is going to access this one, none of them are adjacent, they're all then sequential. That's when you do the transpose, where you change the thread mapping to instead, for B, map B. Yeah, so as you load the tile of B, you transpose it. So you access it in global memory, adjacent threads like the row, and then when they read it to the tile, they read it on columns, and then when you later access it along the shared memory. So I don't quite know how the map. Like, I need to get my head around the mapping in Triton, but it's the same idea. It'll be the same idea where you're trying to reuse an element that you're really using it on columns, but you're trying.
And that one would be
changing this. Yeah, I think
it would
so.
look like this. Group of emerald.
Even if it doesn't come up with a good, I think.
I do sit with the Triton a bit more because I'm not. CUDA, I'm used to like thread level control. So, like, I can say what's going to be in the cache and where.
Moving around in CUDA
Like over summer.
for your job.
No, it's what I realised about 2 months in. I wish I had been doing for my job. But I had 2 offers. I took the wrong one. I took the one that was like ML wearable stuff, and I realised very quickly I wanted to be doing ML system stuff, and that was the other offer. I want to do a PhD. I want to do a PhD. Yeah. But then it would be like I'd want to do DeepMind stuff or like frontier AI. A mixture of like algorithm research, but also like the PL side, so like PyTorch compilers, like stuff like that's quite cool.
You still want to keep it?
Yeah, I want to. I'm planning on taking either custom or ADS.
Okay, actually.
I want to understand the hardware stuff.
You and
You need some
Like,
the target.
like, do you understand symbolic arrays by using anything
Think
right
about how you do this follow.
I'll do that with advantage. Because I want to understand how to do the hot I think a long time I'd rather
take ACA.
ACA is so good. Yeah. But it's too late now, right? Unless
Yeah, no, I audited it and I wasn't sure I would.
it's honestly it was for ML and I was like, so I did both last year. ACA was the biggest surprise to me because I didn't at that point wasn't expecting to get into low level stuff. I was like, high level ML, do some fun maths, create some models, happy days. But ACA really got me into it.
He's like, I'm not telling you.
But actually, you know what?
So ACA is not relevant to ML other than one lecture on GPUs. ACA is
plenty of.
This is basically
ML.
This is basically ACA for ML.
Yeah, right.
ACA is entirely how can you get a decent CPU?
Yeah.
So you do how do registers actually work in a CPU?
Yeah. Like branch prediction, the whole thing.
Yeah, branch prediction, speculation. You do what are they called? Meltdown and vector.
Each group. We're doing like group by group.
Related to vulgar
No, it's vulnerabilities. So how can you access someone else's memory? How can you trick the branch predictor into another branch while you're in another one's running, and then how you can time access in the cache to work out what was in their memory. So it's like really cool stuff. What else we do? SIMD stuff. There was a bit on GPUs, cache coherency and multi-core systems. That was quite cool. It's a really good model.
Yes, because this kind of column major, if you look at how it's PID.
Yeah, I mean in the exam it's just one of those where you just.
Because this is just PID.
So it's not.
Well, it's a poor exam, so we like to. It's a good exam in that it's not just have you memorise everything in the course. It's I'm going to give you some new processes you've not seen before, and let's just have a think about what's going to happen. Yeah. It's pretty good.
But I also thought, okay,
it's a hard one.
In hardware, I'd much rather take.
Well, MML is different. MML is just very mathsy.
Yeah, no. But it helps you at least for stuff like.
So the basic idea is.
Has he changed it this year to cover Gaussian processes? Because he didn't do Gaussian processes last year.
It covers Gaussian.
Yeah. But
briefly.
No, we didn't get. We basically. My takeaway from last year was basically the important thing is empirical.
Normally, why we can't just
likelihood maximization.
Let's say this is the optimal.
Likelihood maximization, you'll get to it. It's basically still probability.
Yeah.
Like how do you derive binary cross entropy or continual cross entropy or least squares as like the correct function to be using?
Okay, I thought it was mostly about what sort of maths is used in machine learning, which kind of is.
Yeah, I mean, it starts out with like classic calculus, and then it gets to a lot of complex stats. It's quite cool.
Would you say it's
The only thing I think that crosses over is when we were doing the DAGs for backward passes, and you just needed to know which way around the matrix multiplications went for the gradients, right? Like, I knew that because of MML, but other than that, MML is very high level. Like it's just. But it's still useful. It's interesting. It's still useful. Yeah. What about you? Are you looking for jobs at the minute?
Not really.
Yeah, you can do it.
Stressed a lot last year, so I was like,
this is one way.
do the same thing
I
this
actually
year.
explain in my lecture.
But I don't want to lose
One way is doing just swap.
training momentum. I keep applying, but
Corresponding.
realistically, I'm just applying stuff I don't really mind getting.
Okay.
Just to like, okay, I'll
practice.
So they
kind of.
do other optimization techniques.
If you were to apply to stuff you want,
If I were to apply
So
stuff, I
actually,
really like.
we are doing this.
Exactly.
We are doing this because we can apply some
Yeah, apply that later. But this is just. But this question asks you to do.
Very good
they are.
in terms of
For this program, so you
architecture
have to do this.
and shared
But you are right. If the
shared
our
board,
purpose
shared
is to
memory, that sort of stuff.
row major, column major, memory.
They usually
class,
take
and
over
you
experienced
can just
people.
swap.
Yeah.
Okay. Yeah.
And yeah, for now, hopefully I'll get. I took a project from Win.
Which one? Was it this one?
No, it's
Yeah. So this is the question you
like
just asked.
smart switches.
So in this
computation,
example, let's the
PGA, smart switches.
in general, let's say wedges multiplication.
Some guy previous year did
So usually, let's say this is
multi-level Monte Carlo. So I'm just looking at. I think that's where an math for ML might come helpful. Come to see where I can find those.
one row. On cache.
Yeah, I was looking what's happening
Try
in the
to-
center in learning. Maybe you can offer like the virtual privacy calculation onto. Interesting. I mean, yeah, like differential privacy sounds very cool. You read Matthew Wicker's paper on differential privacy? No, I still don't understand, but it doesn't seem it's like okay, so very simple computation, but with because of probabilities, it achieves a lot of
Yeah, I should be able to.
yeah. So him and Matt, you know Calvin say that you do contact. Yeah, so him and Calvin do a lot of stuff. He was the first I spoke with for projects. I really because I was asking about his GPU framework for foundation.
Email it to you.
I was like, I really like the work him and Matthew do on like interval bound propagation for satisfying various things. But so a lot of their research stuff is interval bounds over the ground. Oh, you mean their paper together? Yeah, I was one of my projects that I picked.
So
You can see what you're doing now.
For learning.
You can plug that in when you.
More advanced, but basically you're taking interval bound and see if you can fit it into a GPU computation. Understand? It's how do you like their paper? It's how do you do?
I'm just taking it out.
Well, their paper relies on doing interval. How do we typically do that on a GPU, given that very similar to you?
How are you?
Okay, thank you. What are you?
If I hadn't something. See you.
How was that?
Okay, I will make it to the
How was
Kind of useful there. I didn't know. Level up, but operational. He was out of so I was like, I'm probably not going to propose that.
I'm sure offline samples.
To take from that one. And then what elements for optimization? No, just like structure preserving.
Just give me 2 minutes.
You know, which is just like
right?
IOP and big integers, like pure.
Let's say you have to cache.
not built?
You're
So not built. It's brand new.
It's not something
It's actually not ready until
you load
February,
this
March.
one.
So I literally not long way to wait, but you know, salespeople are like they're right, you're buying it, and it's like, well, I haven't seen it. They're like, well, it's going to be gone.
If you kind of
So it's mad. It's like you buy it like 6 months before.
multiple rows. Multiple rows.
So you
can basically
just like she spent all this money on something that.
Hi, Zach.
columns of it.
Yeah,
You
yeah.
cache them and you just do it.
Good, thank you.
You maximize the data.
Yeah,
You just you're using this A. In the original case, you're using A. But not
Plastic out the other way.
You're not.
Against the flow.
It's not able to cache the whole thing.
Realize that
It's done now.
Yes.
Yeah, it'll be nice.
Yes, that's the key assumption.
I hope it's nice. If they build it to how it should look. Yeah, yeah. By the CGI images.
Why it's grouped out
Yes, we will see.
in some cases. Yes.
Took their phone.
Thank you.
So far away. Yes. Where are you? You're east, right? Chigwell, yeah. It's really in the loop. In the loop. Is it at the end of the loop? I remember going to Ilford.
It's around the faculty. Set up.
Yeah, everything is.
Yeah, Ilford Central Line as well.
Her laptop is locked, so we can use it.
Okay.
Central?
Ilford.
Let me find the one. Let's find the one.
I also had an email last week from someone at the University of Bennett who was asking if they could join any of these that get live streamed.
Look.
Oh, no.
Yeah, that's the one.
Yeah, that wrong.
Ilford is Elizabeth. Is that where Jordan is? No,
Jordan is in Romford.
Romford.
Further.
Yeah. Okay, yeah. So you're Chigwell, right at the end of this bit. Oh, yeah. If you go this way, it doesn't work, right?
I might as well. If you do anything, let you know. Hold your breath.
Because I remember even Fairlup was.
Just I'm worried that that will discourage people from attending, especially the one who come. Even people from the same campus ask me, "Oh, is it gonna be in-person only?" I'm like, "Yeah, because
That's what I did. It was one of my ex-partners.
from like City Guild building to Hats.
I was
Venice,
headed
Milan.
down, go to Stratford and then take the tube to Fairlock. But even that, which shouldn't look that bad. Hour.
The station is like near like
Nowhere.
How's your week going so far?
I started teaching on Monday. So
Very, very enthusiastic. I'm good. How about you?
not too bad, not too bad. How's the term been?
Just a send.
Yeah,
I had like one really intense week, and then it was quite chill.
Yes, we're not
Enjoying the chill part.
enjoyed the last term. Yeah.
How about you? Is it half term?
It's half term now. Yeah. So it's always a bit frantic the first half term because it's sort of UCAS season.
Oh, okay. Yeah.
But
coffee after.
now that's all the university's problem now.
And I guess a lot of the Imperial Maths will be free for the places to do it early. And
Yeah, exactly. So, I can't remember how many, but it's something like 50 out of
We do need to do some work in that gap. We go through
a minute ago. So yeah, they've had all their entrance exams and things like that. So
just keeps
how they do.
it's very exciting. What are you teaching? Do you split up by class or by module?
Yeah, so we teach like maths and further maths as like one subject, and then we have like a pure strand, mostly stats strand and a mostly mechanics strand, and we also have like every week each student has like an hour of problem solving.
And the week teaching for that.
Just TMUA, that kind of stuff. Or in year 13, it shifts a bit more to like, here are some topics that you studied last year. Here's like a range of different problem topics. So I'm teaching year 12 pure, year 13 pure, some mechanics as well.
Hi, Thomas.
Some problem solving.
Extending the gym.
That's this year.
Now going to be
Most people on the team kind of a bit of variety, like
its own the share. And the JMCs were always just like, and now they're going to have their own program.
let me just make sure I'm
Operational. But there might be more roles available that might ask for something computational.
I think Marianne had that problem last
Yes,
year.
I saw
where it was
her
always
earlier.
adults.
Yeah, she said it clashes with her teaching.
even in the call so.
Suggested if she wants to join for a
I'll just
work.
It can suck a visa, right? So
Hi, how are you?
we could do visa and deal with that. You're not going anywhere.
that's just like
at school level, exactly. Right? Bar a few teachers that would be honest. They don't want you off us at school.